and electromagnetism out. Now, if this is your first time, and I can see some familiar faces already here, but if this is your first time, then thanks for coming. Ask questions whenever you want, and you can steer the kind of direction and speed that this is going in by just throwing in your comments, and we'll be constantly checking what you're saying. And feel free to get involved. Don't worry about getting stuff wrong, because we all get stuff wrong all the time, and I'm pretty sure I got something wrong on one of the last ones. That's just the nature of learning things. Yes, today is high school physics, and it's kind of aimed at people ages like 13 to 17. We're just going to go over the key concepts about magnetism and electromagnetism, so it doesn't actually matter which school you're in or what country you're in. It's all the same kind of stuff. Let's start with this. This is a robin, and this robin is wearing an eye patch. Now, my question to you guys is, why would this robin be wearing an eye patch? Now, this robin was caught by a paparazzi and wearing this eyewear. But why would it be wearing it? What possible reason could the robin have to wear the eye patch? And if you can't think of an answer to that, what effect do you think it might have on the robin if we switched the eye patch to the other eye? So if we moved the eye patch over and we popped it here instead, and we revealed this eye, then it's like sort of like a robot robin now in quite a scary way. But anyway, if we were to switch the eyes around, then what effects do you think it might have? So Jack is saying, is it missing eye? So no, this isn't necessarily a missing eye. Pumpkin Master is saying, see better in the dark. So I don't think this will have any effect, switching the eye patch, on how well the robin can see in the dark. Although I guess if it's wearing the eye patch all the time, it might train that eye to be more sensitive, perhaps, to light. I'm not sure. Although actually, that's a problem. If you wear an eye patch as a baby, then you become much worse at seeing, because you need, as a baby, to be absorbing visual information to develop what's called the ocular cortex, the part of the brain at the back that processes all your visual information. So you need to see at a young age in order to develop that. Otherwise, you might have functional eyes, but you can still be actually blind because your brain hasn't developed in the right way. Big problem with being a baby in a cave. Okay, so no one said the answer, which is fine, because actually this is a really weird answer, but I was just wondering if anyone might know. Robins can see the Earth's magnetic field almost as if it's a colour. So if you're a robin and you're flying around the world, then you will be able to see in the direction of north and in the direction of south, there will be something that might manifest itself as like a colour or something. We don't know, because we can't get inside a robin's brain, but we know that they have an ability to detect the Earth's magnetic field that has something to do with their eyes. And we also know that only one of their eyes is connected to the part of the brain that can process this information. And so if you put an eye patch, I'm pretty sure actually that's on the right eye, then a robin can no longer see the Earth's magnetic field, and then loses that element of its ability to navigate. Now, birds don't depend 100% on the Earth's magnetic field to navigate, but it is important for a lot of birds, and so taking away the right eye of a robin can be really problematic for them. Pumpkin Master saying, are there other animals that can see the Earth's magnetic field? And yes, there are other animals, that's true. There are a lot of birds that can see the Earth's magnetic field, and there are also other animals like loggerhead turtles and monarch butterflies that have some degree of what we call magnetoreception, which is just a long word for being able to kind of perceive the Earth's magnetic field. Magnetoreception. It's pretty cool, I think, that robins can see the Earth's magnetic field. I wish I could see it. But, this is actually one of the really fascinating things about magnetoreception. If you ever want to, this, by the way, is the topic that I did my final thesis on at university. So this was, the thing that I did most of my studies in. So I can answer loads of questions on this if you throw them my way, but I should probably get on with magnetism and electromagnetism. But one of the really fascinating things is that our eyes actually have really similar machinery in them to robins' eyes. When I say machinery, I mean the kind of biological stuff that we've got in our eyes. We have the same kind of stuff that theoretically could allow us to see the Earth's magnetic field. It's just that we think that we just don't have the kind of processing power to deal with it. I'm Not to say that we aren't smart, because, many would argue that we're smarter than robins, and many would argue that we're not. Here's the robin's brain, wired up to the eye. But for some reason, that part of their brain is developed in ways that ours hasn't. Okay, anyway, right, enough of these robins that can see the Earth's magnetic field. Let's go down and look at the Earth's magnetic field. Right, so here's the Earth. Who knows where the North Pole of the Earth is? Is it number 1 or is it number 2? Where is the North Pole of the Earth? Now, while people are answering that, just very quickly kind of want to welcome people who have arrived late. Thanks for coming. This is an Aim High Live, so ask questions whenever you want. We're going to cover high school physics, magnetism and electromagnetism, which is aimed at ages like 13, 17-ish, but if you're older, doesn't matter, because you can catch up on the concepts, and if you're younger, some of these things you might find a bit hard, but others you probably won't, so just see how much you can keep up with, I suppose. Okay, so Vendible Sugar is saying 1, and no one else has answered this question, as if it's an insulting question for me to ask. But actually, the reason I asked where the North Pole is that it's kind of a trick question, because the North Pole of the magnet that exists inside the Earth is at the bottom. So the North Pole of the magnet is at the bottom, and the South Pole is at the top. Now, the reason why we refer to the top, well, I say top of the Earth, obviously it depends where you're looking at the Earth from, but the reason why we call the top the North Pole is because if you get a magnet and you float it on some water, or you dangle it from a string or whatever, and you allow it to like spin around so that it faces in a certain direction, the North Pole of your magnet will face towards what we call north. So your North Pole will face that way, and your South Pole will face that way. But that's because your North Pole is attracted to the South Pole at the top of the Earth. So actually, I know this is a bit weird, but the Earth's magnet is the opposite of what we say it is, which is why our North Poles are attracted to the north. So yeah, Xenon said number 2, which is spot on. Right, so obviously there isn't like a physical bar magnet inside the Earth. Does anyone know where the magnetism inside the Earth comes from? What is it a consequence of? Wonder if anyone knows. And while you guys are saying that, I'm just going to start to draw on what we call field lines. So let me just get rid of this North Pole label. Okay, so wrong thing. So field lines come out of the North Pole, and they go round and into the South Pole. And there will be, let's do a couple of these on each side. So let's do another little north one. So these are not the neatest drawn things, but it's a start. So we say that the field lines, the lines of magnetic field, come out of the north, and then they go round until they go into the South Pole. And likewise, they come out of here, go around this way, and then go into the South Pole, and same with here, and same with here. Now, I just want to stop at this point and say, the Pumpkin Master's saying something in the core, isn't it iron and nickel? So yeah, the iron rotating in the core is what causes the Earth's magnetic field. So we've got this molten rotating core of iron, which is what Mars lacks. Mars's core we think is solid, and that's part of why it has no magnetic field. It's also part of why it has no force field, because the magnetic field is a force field that protects us from high-speed particles coming from the sun and stuff like that would otherwise blow away our atmosphere. So all these high-speed particles from the sun get deflected to the North and South Pole instead of being fired at the Earth and kind of blowing away our atmosphere. And so that's why we still have an atmosphere, and that's why Mars has no atmosphere, and it's part of why Mars would be such a rubbish place to be. Like, Mars would be so much worse than being in the Antarctic. It'd be awful because there's no atmosphere, and so it's just like exposed to the cold vacuumness of space. Well, I say no atmosphere. It does have some atmosphere, but it's just very, very, very thin. Anyway, yes, so our rotating iron core is what gives us this magnetic field, and that deflects the particles to the north and the south, which causes what effect in the North and the South Pole? What effect is caused in the North and the South Pole because of all these high-energy particles that get deflected there instead of blowing our atmosphere away? Now, while people are saying that, this is what I just wanted to say quickly about magnetism. So magnetism is really mysterious. It's one of these things that, like, we understand a lot of things kind of around how it works, but what it actually is still something that we have a long way to go to really get to the bottom of. It's kind of like energy and it's like charge. These are things that we know how to work with, and we know how they kind of relate with one another, and we understand some kind of rules about them. But actually, most of the things about magnetism we still just don't really know. And I remember there was this amazing physicist called Richard Feynman, who he was so good at communicating stuff, and he used to love like communicating physics ideas, and he did this great BBC interview, and he was giving amazing answers to like all of these different physics kind of questions that was being asked. And then as soon as he was asked about magnetism, he just started like slowing down and kind of not really giving a very coherent answer. And obviously it must have been frustrating to him to explain it because it's so complicated. Like nobody really knows properly what it is. Anyway, yes, so VS is saying it's going to be the Northern Lights. So yeah, the Northern Lights is caused by these high-speed particles being deflected to here, and then the Southern Lights down here as well. Cool, right, so just a quick point about field lines. So the way we represent these magnetic fields, that again, we still kind of don't really fully understand too much about them, but we kind of try to get our head around them. The way that we understand these magnetic fields is by drawing these field lines, and the field lines go from the North Pole of the magnet to the South Pole of the magnet. What I want you to notice is where the field lines are closest together. So compare these two regions. I want you to compare this region here, and I want you to compare this region here. So in region A or B, which one do you think has the strongest magnetic field? Region A or region B? Which one has the strongest magnetic field? Let me know what you think. So Karina is saying region A. Yeah, perfect. So region A has the strongest because the field lines are closer together. So with magnetic fields, we kind of look for where the field lines are closer together, and that gives us the impression of a stronger field. And at B, the field is weaker. So yeah, the magnetic field is going to be strongest straight above the poles here. Now, if you're a bird, like a robin, then this is the kind of field lines that you see. I'll just explain this really quickly because it's interesting, but I won't spend too long on it. But if you notice here, the field line is kind of parallel to the surface of the Earth, whereas here, the field line is kind of like perpendicular to the surface of the Earth. It's going straight into it. And kind of all the way in between here, the field line is at a different angle relative to the Earth. And in the UK, the field line is kind of... In fact, north is pretty much straight in front of me, so the field line is kind of like this. So it's going that the field line goes uphill towards the equator and downhill towards the pole. And we think that these birds can't really tell the difference between north and south, but they can see that the field lines kind of go downhill towards where it gets colder and uphill towards where it gets hotter. Anyway, I won't spend too long on that because we could spend ages talking about birds, and we need to cover magnetism and electromagnetism. And oh, T and Jack also got A. That's great. Right, so let's go to these two magnets. So something that you're often asked to show that you know how to do in physics is show that you can draw what's called a uniform field. So I was already showing you that a magnetic field kind of goes out from north and into the south, and that you can draw multiple field lines like this, and obviously where they're more bunched together towards the poles, these are the regions with a stronger field here and here. However, if you bring two of these magnets quite close together, like this, then some of the field lines coming out of north can immediately just go straight into the south here. And what you end up with is these really nice straight lines, these straight field lines that go from north to south, from one to the other. And this is what we call a uniform magnetic field, because at all regions between these two magnets, so at every single point between them, like whether you're here or here or here, it doesn't matter, the field strength is exactly the same, because all the lines are exactly the same distance apart and they're all running parallel to one another. Now, obviously, the field strength is going to get a little bit weaker if you kind of go further out here, because it's kind of starts to get slightly further apart as it's taking more of a loopy route, and then eventually other bits of field line are going to kind of loop around in that direction. But anyway, you need to know that you can create this thing called a uniform magnetic field here. Right, next thing. So, I'm going to show you these pictures. So here we have this is what's called an electromagnet. which means if you haven't encountered it yet, I mean, we're about to cover it, but it's a magnet that you can turn on by turning on the electric current, and then it will pick up things like these metal objects in the scrapyard, and these are fridge magnets, which are permanent magnets. So one of these magnets is a hard magnet, and the other one is a soft magnet. So which one is which? Do you think A is hard or B is hard? Do you think A is soft or B is soft? Which do you think? Which way round are these magnets? Now, you might not know what this idea of hard and soft means yet, but I'm just kind of interested to know what people think first, and then I'll explain what it means. What do you think? And again, for anyone joining late, this is the Name High Live, so you can ask questions whatever you want. The point is to go through some of the key physics concepts in this one, but if there's anything in particular that you really want help on, just throw it in and I'll give you a go. Okay, so Jack thinks that B is hard and A is soft, and that's perfect. Yeah, good. So yeah, B is a hard magnet and A is a soft magnet. Now, what this means is that, well, it's not that the magnet is hard or soft, it's that the material is hard or soft. And by hard, it means that once you've turned it into a magnet, it stays as a magnet. So these fridge magnets just stay magnetized for many, many, many years. And they will just remain so as long as they're not kind of heated too much or dropped on the floor. They'll remain as magnets for many, many years. Whereas this electromagnet is soft. And what that means is that it can easily be magnetized and very easily demagnetized. And that's really important because when you turn it on, all this stuff is going to attach to it. And then when you turn it off, you want it all to drop. And if it doesn't drop, then the magnet is not really doing its job. Okay, right, let's scroll up here to this. Has anyone ever seen this stuff before? Do you know what this is? It's really beautiful, and you can actually make it quite easily by yourself. I made some once and it was really messy. This stuff is called ferrofluid. And it's really beautiful. It's like a... I wish I wanted to show you a video, but it was really hard to find one that was decent and have loads of talking over it. But it's basically like oil that's got loads and loads of tiny, tiny pieces of iron inside it. Loads of tiny pieces of iron. And what happens is when you expose it to a magnetic field, there's just a wasp that's appeared in front of me, threatening. I need to get rid of it. When you expose this stuff to a magnetic field, all of these little pieces of iron will become magnetized. Now, if we look at one single spike, the reason why they turn into spikes is because, let's make the spike bigger. Each spike, the iron inside it will form one of the poles. So let's say you're exposing it to the North Pole at the bottom. Let's say you've got a big North Pole magnet under here. The bottom of the ferrofluid will become a South Pole, and then this spike will become a North Pole. But because all the other spikes are becoming North Poles as well, they all repel one another. And that's why you get this really beautiful splitting effect that looks like a hedgehog, because there's loads and loads of North Poles all kind of cramming in together. And it's really amazing the way it like moves across different surfaces. I love ferrofluid. Anyway, right, it's time to start telling you guys about electromagnetism. So, who knows what this is about? Why have I brought this thumbs up smashing through the page into view? What does this have to do with electromagnetism? What do you guys reckon? And maybe this is not something that people know, which would be fine. Okay, I'll start explaining it. So this thumb represents something called... Thumbs up to the black stuff. No, this thumb represents something called the right-hand grip rule, which is one of the most important rules in electromagnetism. So I said to you before, right, that magnetism and its kind of relation to electricity is something quite mysterious, and it's something that we are still like making progress in understanding. And we have like really, really great laws now that kind of interlink these ideas and expand it into all kinds of other areas like quantum mechanics and all that kind of stuff. But still, it's kind of weird why it behaves in the way that it behaves, and it's still something that we don't quite really have our heads around. But ultimately, the thing that that we often start by learning in physics is this relationship that tells you that if you've got an electric current flowing down a wire in a certain direction, so represented by the thumb, I'll just do kind of rest of the blue line going out the back of the hand, then you will form a magnetic field that will spin around it in the same direction as these fingers. So if the magnetic field is going upwards, if the current is going upwards, then the magnetic field will spin around it in an anti-clockwise direction if you're looking from above. So any wire in your house that is carrying a current down it will have this spinning effect, unless it's got a current going forwards and backwards down it, in which case it'll cancel out. But any wire in your house that's got current traveling in one direction will have this magnetic field spinning around it like that. This is why electricians can often like detect what's going on in a wire by like putting a little kind of metal case around it, because they can just detect the magnetic field that's around the wire. So let me just label those things up. So if this is the current, then this green line will represent the magnetic field that gets formed. So you get this magnetic field that, as I said, like forms in a circle around it. Okay, here's a question for you guys. I've got, if we get this red wire here, so I've just continued the red wire. This is a part of a full circuit, and I just haven't completed this circuit. But if we just look at this bit of red wire here, so we say that the current, which I'm going to start representing with I, because I is always the symbol we use to represent current, which is weird, but it is. Anyway, so if the current is flowing in this direction, then can you guys try to visualize, take a moment to try and imagine what the magnetic field is doing around that current? So you've got this wire traveling in this direction. So in this direction, what is the magnetic field doing around it? So take your thumb and your hand and try and visualize this image. I guess this probably looks like my left hand to you guys, the way that it's broadcasting. So I guess I should use this hand to represent a right hand grip rule. Yeah, I hadn't actually thought about that. So it will, if you're looking down from above, then which direction will the magnetic field be spinning in? Anti-clockwise or clockwise? What do you think? So Venerable Shig is saying, yeah, anti-clockwise, exactly. So same as this. So use our right-hand grip rule, and we show that it's going to spin in this direction, anti-clockwise. Cool. Right, now, what if instead of just a straight wire, you've got this blue one? Let me just grab it and move it down a tiny bit. So instead of a straight wire, we've got this blue wire here. Now this blue wire is going in a circle, so it's taking the current, and it's moving the current around in a circle and then back out this way. So if you look at any point on the wire and you use your right-hand grip rule, then you can see at this position here that the current is going to be going up from below and then down like that, so down through the middle. And if you were to do the same thing on the other side, then it would show you that the current is going around this way and then down that way. And similarly, over the top, it would be like this. Now, what this means is that overall, there is a magnetic field in the middle of this coil of wire that is either going into the page or out of the page. What do you guys think? Is this magnetic field in the middle of this coil of wire going into the page or out of the page? What do you reckon? T and xenon are both spot on with anti-clockwise as well. So Jack thinks in, Venable Sugar thinks in, xenon thinks out. So because we've got the magnetic field coming up here and then plunging down here into the middle, and so it's going up from here and then plunging down into the middle, up from here and then plunging down, it'll be going down into the page in the middle here. So it goes into the page here, and if you were to look outside the coil, then it would be coming out of the page. Now, if you were to flip the current around and it were to go in the other direction, then obviously it would come out of the page here and vice versa. Okay, right, now let's look at this coil of wire. So this is a coil of wire. It's just a wire that's in a coil, but for some reason, physics has decided to give this a complicated name, which I will tell you, but it's unnecessary, and you can probably just keep calling it a coil for the rest of your days, and you don't really ever need to call it a solenoid. But solenoid is the other official word that is often used in books to represent a coil of wire. So there's a coil of wire coiling round, 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 round. What I want to know is, in this bit, so right, I'm going to introduce you to a new way of drawing things now, which you may have seen before, but in case you haven't, here it is. So if you can see from this spiral, here the current is coming kind of out of the page, and then here the current's kind of going into the page. So into the page, and then kind of out of the page here again, and then kind of into the page down here. Now, how we often represent this, coming out of the page, we do a circle with a dot in the middle, and going into the page, we do a circle with a cross. And the reason why is because it's kind of like an arrow. So let's look at this one here. If an arrow is firing towards you, then what you see firing towards you is the point in the middle of the arrow and then a circle of the arrowhead. Whereas if the arrow is flying away from you, then you look at the arrow and you see the crossed tail feathers as it flies away from you. So this means going into the page, because that's the crossed tail feathers flying away from you, and this is coming out of the page because that's the point of the arrow flying towards you. Okay, so if you have the current coming out of the page here and going into the page here, and let's continue this picture to see out of the page here, into the page here, and so on, then which way will the magnetic field be going around each of these top points and around each of these bottom points? So can you tell me around the top points, will the magnetic field be going clockwise or anti-clockwise? And tell me about the bottom points too. What do you reckon? So in case anyone needs reminding quickly, the right-hand grip rule, you use your thumb to represent the current, and then your right fingers, although actually it would be this hand, I guess, and then your right fingers would represent the magnetic field coiling around that in a spiral. So these top ones, you've got the field coming out of the page, and so as Jack says, perfect, yeah, top is going to be anti-clockwise, and the bottom is going to be clockwise. Now, what you might notice is that as a consequence of this, on the bottom, in between the coil, in the middle of the coil, this field's going that way, this field's going that way, this field's going that way, this field's going that way. In the middle of the coil, you have this strong magnetic field going straight through the middle of it like this. And then, of course, just like every magnetic field, it will loop round to where it started and repeat like that. But what you've essentially created here with this coil of wire is a north pole and a south pole. And so this is essentially how an electromagnet works. All you need to do to make an electromagnet, and it's so easy to make one at home, is you just take a battery and you just coil up a wire around a nail, for example, and then you connect it to the battery. And as long as the coil is only going in one direction and doesn't double back on itself in a way where it ends up kind of pointing in the other. Well, as long as you only coil it in one direction, then it will always produce an electromagnet if you connect it to a normal battery. Now, to make an electromagnet stronger, what can you do? And I can see that T was spot on as well with the top and the bottom. So if you want to make your electromagnet stronger, what can you do? And while people are writing the answers for that, I want to point out something else. So I told you about this right-hand grip rule as if the thumb was current and the fingers were magnetic field. But actually, if you look at this coil of wire and you line up the same hand, your right hand again, if you line up the fingers with the coil here of current, then you will see that the magnetic field goes in the right direction as well. So actually, you could do current with your thumb and magnetic field with your fingers, or you can do it the other way around. So if you've got a magnetic field that's pointing straight upwards, then that means that you must have a current that is going in this spiral around it. So actually the right hand grip rule is really, really versatile because you can use it both ways round, and it gets so useful in physics. It's something that like all the time that I've been studying science, I've been using this rule. Because it's the core rule that links together that idea, the right-hand grip rule. Okay, so how do we make this electromagnet stronger? And obviously this page is getting quite busy now, so I need to kind of move out of it. But yeah, if you want to make it stronger, then you add more coils. Yes. You increase the current. Yeah, so you can make your current stronger, and that'll give you a stronger electromagnet. And the other thing you can do, which I'm not sure anyone mentioned, is you can add a soft core. So when I say a soft core, I mean like a piece of iron or something like that can just sit in the middle of your coil, and then the piece of iron will become magnetized itself because of the coil that you've wrapped around it, and that will become the electromagnet. So when we see these electromagnets picking up scraps of metal, these things are just a big old piece of iron sat in the center somewhere. I can't see that because I'm drawing in white. So you've got a big old piece of iron sat in the center somewhere, and then wrapped around it over and over again, you've just got this coil of wire with thousands and thousands of loops just going round and round and round to make it as powerful as possible. Right, okay, so let's now go down here to a slightly tidier part of the board. So I'm gonna ignore this left-hand thing just for a moment, because I'm gonna come back to that in a moment. But first, I want you guys to think about this problem. So if you've got a north pole and a south pole of a magnet, and they're both facing one another, and in between them you've got a wire, and this wire here is connected to a circuit, so it's like connected to a positive end on this end and like connected to a negative end on this end maybe, then because of that, you could say that the current is flowing into the page. So because it's flowing into the page, we give it this symbol to show that it's like the feathers at the back of the arrow, it's flying away from us. So this is a current going into the page. Now because this current's going into the page, which direction is the magnetic field going to be going around that wire? Is it going to be going clockwise or anti-clockwise? What do you think? Venable Sugar is saying clockwise, which is perfect. Yeah, great. So the magnetic field is going to be going clockwise around this central wire. Now, at the same time, you've got the magnetic field of the magnet going from north to south. So the magnet's magnetic field is just trying to create this uniform magnetic field that we were talking about before. And it works towards the edges, but at some stage the magnetic field starts getting deflected by this other magnetic field being generated by the wire, like that. And so the magnetic field lines, instead of just going straight from north to south, they kind of go around the whirlpool that's being created by the wire, and you get this effect. Now, as a consequence of this effect, the wire will actually start to move. Which direction do you guys think the wire will move to try and straighten out these magnetic field lines? Which way is the wire going to move? Up or down? Perfect. Okay, so everyone's saying down. Exactly. So the wire is going to be forced downwards. So this is the beginning of starting to see. This is actually how electric motors work. They have a wire carrying a current inside a magnetic field, and because the wire is carrying a current, it gets forced in a certain direction. So it will be forced downwards because the magnetic field lines are trying to straighten themselves out. Right, now instead of drawing all of this stuff every time, which is quite complicated, instead this guy called Fleming came up with this rule with his left hand, which I'll show you here. So what he does is he uses his first finger to represent the field. So first is for field. So that is the magnetic field that's in place. Magnetic field. And then the second finger, this one, second finger, represents the current. So the first finger is the magnetic field, the second finger is the current. And I'm just going to delete second because you can just remember that second. So yeah, the magnetic field and the current. And then the final finger is... the final finger is then the thumb is like the thrust, or it's the direction of the force. So it's the way. So the thumb is the result. It's the way that that this wire will end up moving. So if you try and use your left hand on this problem, you'll be able to line up your first finger so that your first finger is pointing in the same direction as the field. So it should be pointing from north to south. And then you need to align your second finger so that it's going into the page. So I guess that would be that way around. And then your thumb, if you manage to do that, I've given a really awkward one to do, it's probably easier to do it at a different angle. But if you manage to find a way to do that, then you will find that your thumb is pointing downwards, showing that the wire will move downwards. The key part of this is that you just have to keep all of your fingers at perfect right angles to one another. And as long as you do that, it will always work perfectly. So you line up your first finger with the magnetic field, your second finger with the current, and then your thumb will show you the direction that the thing moves in. Right, okay, so to see how much people have understood this, let's give you guys a problem to try. So let's now switch this up a bit. So here we're going to have the South Pole, here we're going to have the North Pole, and let's just have a wire now that is just going to run like this, and the wire is going to have its current flowing downwards. So the current here is flowing downwards from the top of the page to the bottom of the page. Now, my question to you guys is, how does this piece of wire move? How does this piece of wire move? What do you think? Now have a go at using your left hand. Try and line up your second finger with the current, so make sure your second finger is pointing downwards into the down along the screen, and your first finger needs to be pointing from north towards south. So which way do you think this wire will move? So T's saying down, Minimal Sugar saying up. Actually, I think it's gonna move either into the page or out of the page. So I kind of want to know which one of those you think it's gonna be. Because it will never move in the same direction as the field or the same direction as the current. So maybe that's what you meant when you said up and down. You were talking about in and out of the page, but normally when we say up, we mean this direction, and down means this direction. And it won't move in that direction because that's parallel to the current. It's always going to move at right angles to both of them. So Jack thinks into the page, which is spot on. Yeah, it's going to go into the page. So, and yes, brilliant. That's to come through. Great. Yeah, so it's going to move into the page. Perfect. That is really great. Nice work, everyone. Okay, now when you start to, I think when you understand the basics, when you start going on to motors, it starts to become a lot easier to understand why things are moving in the way they are. And I'm not going to cover motors today because it's quite a big topic, but I will just tell you one more thing before we depart the left-hand rule. I will just tell you that when you're making electricity, so when you're using force and magnetic field to make electricity, which is what happens in generators, what I was talking about this on the energy and power one before, that's how we make electricity, is by spinning a coil in a magnetic field. So we use a force to move something in a magnetic field and it generates current. When you do that, instead of using the left-hand rule, because you're making current, you use exactly the same rule but with your right hand. So we use your right hand when you're making current, and that can be a bit confusing, but luckily, like, most schools actually ignore that for a while, and they'll only give you the left-hand rule, and they'll only ask you which direction the wire will want to move in. So that's the motor effect, because you're causing something to move. But just to know, when you're making current, this is going to flip around to the right-hand rule. So that's something to look forward to. Okay, last bit I wanted to do is this, because this is just one of the last topics that you do in electromagnetism, and this is this is transformers. So a transformer is not like as cool as a thing that transforms into stuff. It's literally just something that changes the voltage of a circuit to another voltage, but it's got quite a satisfying bit of maths, so I'll finish on this. And there's actually such a good story behind this about Thomas Edison and Tesla, and about the difference between Thomas Edison, who was like a businessman who just wanted to make as much profit as possible and was all about kind of defeating the opponent and just trying to make loads of money, basically. And Tesla, who was the scientist who actually properly understood stuff and knew that he had come up with the best solution for how to run electricity. And it's totally mad. If you want to read it, it's a really sad story, actually, because ultimately Tesla died quite young, never managing to properly make a success of the research that he did, even though he knew for his whole life that it was right. I mean, imagine going years and years and years being that guy who's like figured out how to make electricity efficient and work for everyone, and then there's just this businessman who just doesn't care, just wants to make as much money as possible, and will feed any lies that they can think of to the public to make them scared of Tesla's inventions. That Thomas Edison made so many lies to try and make people scared of Tesla's electricity innovations. Anyway, obviously now the car company Tesla has been named in honor of Nikola Tesla, because he was such a genius and really weird guy. He used to have like these like such vivid visions, like hallucinations, that he would just have to stop what he was doing if he was at a party or in walking through a park or wherever he was. He would have such lucid visualizations that he would just have to stop and just let them happen and just experience them. And a lot of his ideas came from these quite extreme, weird moments in his life. Anyway, Tesla, cool person. Right, he came up with this. So he came up with this idea that if you have a wire and you coil it around one side of this kind of like, it's like a square of metal. It's like an iron, like a square of iron that you can wrap coil around either side. I explained that so badly. It's just like a square of iron, basically. But I can't remember what the 3D word for it would be. I guess it's like a squared donut would be the best way of thinking about it. Anyway, so you wrap loads of coil around it, and let's say that this side has 30 coils of wire going around it. And then on the other side, let's say you've got loads and loads and loads and loads and loads of coils. So way more coils. And let's say on this side, you've got 120 coils of wire going around this piece of metal. Now, if you feed in a voltage to this side of, let's say, 2 volts, then does anyone know what voltage you'll get out the other side? What voltage do you think you'll get out the other side? And in case it's a clue, this is called a step-up transformer. Step up as we increase the number of coils. Now, while people are working out what voltage they think this might be, I'll just tell you one of the other things that happened. So Tesla invented this, and it was a way that you could change the voltage so that you can make high voltages outside, because when in wires traveling around the country, way more efficient to have high voltage, because it means I'll explain why in a moment, but it means you get to use a low current, which means you don't waste much energy with friction of all the electrons traveling down the wires. So you have a high voltage around the country and then a low voltage in people's houses because it's less dangerous. And he basically figured out how you could switch from high voltage to low voltage, and it could only work if you use basically Tesla's system, which used an alternating current. And Edison didn't have any other patents for that. He only had patents for direct current, which is why he tried so desperately to crush Tesla's innovations. So yes, the answer will be 8 volts. Perfect. Nice work, guys. So yeah, it steps up just in a really simple ratio. And that's the main thing I want you to remember, is that the voltage just steps with the ratio of coils. So in the same way, if you fed 3 volts into this side, then out the other side you would get 12 volts. Because the number of coils were times by 4, and so the voltage would be times by 4 as well. Cool, right, there is one last thing that I want to show you guys, which is kind of going back to something I covered in electricity, but I just want to see if anyone remembers. In electricity, the power is equal to the current times the voltage. So PIV is the way that we often write this. Power is equal to current times voltage. Don't worry if you haven't seen this before. I was doing this in another set of lessons, but I just want to see who does remember this or who can follow. So the power always has to stay the same because you can't create or destroy energy. So if you feed in 10 amps on this side, then what is the power that you're feeding in? So try to work that out. And then the power coming out the other side will be exactly the same. And so my big question is, what current will come out the other side? What current will you get out of the other side on this transformer? So we put 2 volts in and we get 8 volts out. If we put 10 amps in, how many amps do we get out? And this is your last big challenge. I'm going to give some time to see what people think. So Venable Sugar has said 2.5 amps coming out, which is spot on. So let me just talk through why this is. So the power is equal to the current times the voltage. So if you put 2 volts in and 10 amps in, then the power is equal to 10 times 2, which is 20. So we've got 20 watts as the power going in, which means you've got to have 20 watts as the power coming out. So the question is, if power is current times voltage, what can the current be so that when you times it by the voltage, it still gives you 20? And the only thing that makes sense is 2.5 amps. 2.5 amps is the only thing that when you multiply it by the voltage will give you the right power. Cool. Okay, right. Let's stop there because we've covered loads and loads of stuff. And I want to tell you guys about what's coming up next. Well, this is a timetable for what's coming up next. But particularly this evening, well, in like, what is it now, 3 and a bit hours, we've got the Mysteries of Dark Matter with Dr. Sarah Pearson, who's joining us from New York. And she is going to talk about like basically all the stuff that is all over the universe that we have no way of interacting with, and yet somehow forms most of the mass that we think exists. And it's completely mind-boggling what's going on. And she's going to basically explain to us all the models that we think, that we kind of came up with for how we think the universe must work, and the amazing way that so many of them are fit, and how we can use that to see, we can basically see loads of the universe as if we are millions and millions of light years away and looking at it from super far away because of these amazing models that have been built by people like her and her team. And she is really cool and really interesting, and you're going to really like her. So come along to that if you've got come along to that if you've got time, because it'll be great. And then tomorrow we've got more science coming up, some music, and even on Monday Jazz is doing how to compose a pop song, and there's a bit of computer science, and I'm going to start my maths stuff as well next week. So yeah, thanks so much for coming. Do follow the socials if you haven't already, and do sign up for the schedule up here and spread the word, and I will see you guys later on in about 3 hours. Farewell. Bye bye.